Okay, good morning, everybody, and thank you so much for joining us today to discuss fast functional prototyping with freeform injection molding with our good friends Alpine Advanced Materials. So joining us today, we have our friends from Alpine Advanced Materials. And start off, I want to introduce you guys to Jeremy Smith. Jeremy is the Business Development Manager at Alpine. And over his career, Jeremy specialized in custom material markets from everything from aviation to holding roles in sales or production and management of metal parts and their functional systems. He's served across aviation, defense, energy, heavy manufacturing industries, and he holds a bachelor's degree in aerospace engineering from St. Louis University. Also joining us today, right next to Jeremy, is Clifford Green. Clifford is a senior mechanical engineer at Alpine, and he spent the first decade of his career in the telecom industry, designing and manufacturing industrial UPS systems. Now he gets to leverage that experience at Alpine to deliver complete engineering solutions to Alpine's customers. He holds a bachelor's degree in electromechanical engineering from Miami University. Hey, Clifford.
Morning.
Last but not least is our good friend Karsten, who you may have seen before here at Nexa. And Karsten is the business development and sales manager at Nexa 3D. He has been quite the trailblazer in freeform injection molding and is a passionate advocate for what this tool can do for you. It revolutionizes traditional manufacturing methods, reducing costs and time to market without compromising quality. Karsten has more than 10 years of experience in Silicon Valley and holds a master's in mechanical engineering as well as an MBA. But most importantly, he's often accused of being the most curious person in the room. So thank you guys for joining us today. My name is Louis Sims. I'll be your host for today, managing our Q&A, doing the fun slide transitions, all of that. But for the most part, I'm going to leave it here to the experts. And with that, I want to cover our agenda of what we'll be going over today. So first and foremost, we'll do a quick brief overview of what is freeform injection molding, or FIM. And that is just in case you aren't familiar or haven't seen one of our past webinars, we'll cover that quite quickly. The next is, what is the RPM process? This is rapid prototype molding from Alpine Advanced Materials. So this is kind of what bookends the FIM process and really creates a really robust service from the Alpine team. And you also get to see exactly how they're leveraging that for both themselves and their customers. They'll get to cover as well as how FIM compares to conventional tooling, and including some case studies from their customers as well. Lastly, we'll end on a Q&A where we'll try to answer as many of your questions, and I hope there are many. And again, we'll follow up with anyone that we didn't get to speak to during the conversation today. And with that, I'm going to turn it on over to Karsten.
Thanks, Louis, and thanks all for joining at this hour in the morning, and I think, or midday some places. I think, as Louis mentioned, we are all passionate, we are all curious, and I think we are also biased a little bit about what we have seen through our lives as engineers, as nerds, material freaks, whatever we are as background. And I think this slide, I want to just take you into this session that we're starting right now, asking you to join us on this exploration study together with our dear friends at Alpine and their awesome products and projects. And I think if you could just think like this when you think freeform injection molding, or FIM, in short, it's just an ability, an enablement of you being able to work with any design and any material. There will be some exclusions later on, but just think big picture now, any material and any design that you want to work with, and then using injection molding with a twist, freeform injection molding as your manufacturing technology. That will allow you to do a lot of things that you couldn't do. It will allow you to do the same things you did before, much faster, much cheaper, much more iteratively. And that will actually allow you to do things, you learn a lot, you will maybe stop doing a lot of things because it simply doesn't make sense, but now you know. And it could also actually get you to launch stuff to your next milestone, much more reliable, much more data-driven. So on the next slide, if I only had one photo to show in a session like this, it would be a photo of, this is a very organized desktop, but my desktop looks roughly like this after a call with a client. where we've been through what is this thing, freeform injection molding. Well, it's access to materials, it's actual access to strange, complicated designs or regular, hard to do tool-wise designs. And then it's the freedom to choose exactly when to do what with this technology, but not having to be thinking through like a funnel of limited constraints there. Okay, next slide. And I think, why is this interesting? Why is this interesting to Alpine's clients? Why is this interesting to our clients? Why should this be interesting to most? It's because we are, as Louis mentioned, either super curious, super impatient, or we have a hard deadline of reaching some place in a shorter while than normally. And it's because we all have milestones, we all have obligations, we all have budgets and project plans to keep. So we often see our clients being focused on design freezing. With freeform injection molding, you could be unfreezing, by the way, every day. And there are all those reasons why we should be in a hurry, but without losing quality and focus. And then it's back to the, if you could work with any design, why would you then overthink your tool design if you can just print the tool, as the team will show shortly? And then it's also about, what does it cost me to launch the next project? And that's often a prohibitive barrier for doing it at all. So we see a lot of our clients actually start doing things they have not done before, but they did want to do it, but they just couldn't get the funding or the CFO approval to move ahead. So it's also a CapEx reducer and an overall cost reduction to work with freeform injection molding. A few visuals. I mean, I'm biased. I have a poster behind me here on the wall. I mean, I think it's beautiful that you can actually both have tool design and mold manufacturing right there at your doorstep, you could almost say, in-house, service-wise. Call Alpine, call us. It's tools when you need them and in the shape that you need them in on a regular daily basis. Either big tools like the ones you see there on the photo, on the next photo or the next slide. You will also see why some of our printers, the larger ones with the build planes, will enable you to do a lot of smaller parts. And it looks impressive when you look at these, but keep in mind, these parts do not need to be the same. These could be 120 individual, sized up or sized down, bespoke molding tools. And that's kind of some of the unleashing of opportunities, business-wise and technology-wise, that we offer you with the technology here. And on the next slide, I think it's very important and very spot on with the team today. Alpine, they are material experts. They have clients in spaces we can only think about wanting to enter, and it's with that trust and ability to walk up and down a curve of technology. If you look at the left side on this slide, 3D printing is damn good for form, fit, and other tests. And you can use the Nexa 3D printers to print a part in any of the cool resins straight out of the gate, pour it into the vat, and you will have a part in hand. Then later in life, normally you will have to go to molding because now you need certain materials. But with the systems of freeform injection molding that we offer and Alpine offers as well as a service, you don't have to think about that because that gap has been closed. Same units will print parts or print molding tools for molding parts. One has a set amount of resins to use, the other, the molding feedstock gallery. I don't think I'm exaggerating when I'm talking about several hundreds of thousands of materials that you can work with. But that's not of your concern anymore. You just have to focus on, back to the first slide, what are you trying to do differently and what are you trying to launch or know more about? And then on the right side of this one, it's also exactly what Alpine is doing. Are you in a low volume industry, but high performance part? Are you designing in certain materials, properties, testing? It's all up to you. The technology can do what you want it to do. So it's actually back to the drawing table of what are you setting out to do. And that's where Alpine shines amazingly. And on the next and final of my slides, it's also a way of saying, how can you transition? How can you make this transition from an additive space to an injection molding space? And that's where RPM or freeform injection molding as a technology, as a set of systems and platforms will help you cross that leap of faith zone there where everything can happen and most should not go wrong, cost, time, quality wise. And I think, I don't know if we have an animation in this slide, but the idea is to say, if you have additive as at the onset, then you have freeform injection molding or RPM in the middle, and then you go to high volume steel tools or aluminum tools over time if you need it and when you need it, but also with a lot more certainty. So you have ruled out all the false negatives and positives while working with this technology that Alpine will offer you and explain a lot more about in the rest of the session. That was my just quick intro to freeform injection molding. Thanks a lot.
All right, thanks, Karsten. And now we'll jump over to our good friends at Alpine. And so Jeremy and Clifford, if you're ready to go, let's take it away.
Awesome. Thank you, Karsten, for that kind of introduction to the audience for this process. And I'll give you a background on Alpine and kind of tell you why we use the FIM process. So we are a full service design and manufacturing company for typically aerospace and defense. We're specialists in metallic to non-metallic conversion. So we like to use high performance thermoplastics that are injection moldable to lightweight existing systems that are using aluminum, steels, titaniums, et cetera. And the challenge that we found in this, especially in the aerospace and defense industries, is exactly that leap of faith that Karsten just described. The gap between prototyping and full-scale production can be a challenge for legacy systems, for high-performance systems where there is tendency to be comfortable with metals, but not experienced enough with injection molding high-performance materials that can perform as well as metals. So we sought out the process of FIM to build a bridge across that gap from prototyping to full-scale production. And we found, I'll show you a couple case studies in this presentation that give you a picture into how the different benefits of FIM have actually translated to some specific customers. And if you continue on to the next slide, I'm going to have Clifford tell us about the difference between the FIM process and what we call the rapid prototype molding or RPM process at Alpine.
Yes, thank you, Jeremy. The RPM process bookends the Nexa X-Mold FIM process. So here at Alpine, we start with a design for manufacturing using Moldex 3D to figure out different injection molding parameters, your end of fill temperatures, your gate size, and your runner sizes. Then we go into the SolidWorks world where we design the mold. We print it using a Nexa Exip. We then wash, we cure, and then we go to one of our many injection molding partners to inject the mold, and then of course we demold. When we're done with that, though, is we often find out that we need to machine high tolerance features, add helicoils, and then we'll go ahead and coat our parts with different materials like Cerakote, powder coat, even metallizing our parts. So when we're looking at where FIM molds benefit over conventional tooling, there's a long process to develop conventional tooling. There's around 12 steps. It can take up to 12 or more weeks. And there's a lot of cost because there's time. There's a lot of people involved in this process. With the RPM process, it is a very, this is all in-house at Alpine. We can design, we can slice, we can print, we can wash and cure and assemble these molds all in-house in a very small space with minimal tools. And this is what lets us go fast in our RPM process as well here at Alpine.
All right, so I think we're going to, here we're going to start detailing some of the case studies that we've done with our customers. This specific case study illustrates the speed of the FIM or RPM process and how it benefited this customer. This customer is a defense customer that was pursuing a technical demonstration. So they had to demonstrate a system, a UAV system, in actual functional testing for their client. And they came to us with a need for 60 parts in 20 days. They found out that their machine capacity was not going to be sufficient for all the components that they needed to machine in time. So what they did, knowing that we had been working with them on other components for their system, and our unique material, HX5, is specifically designed to replace 6000 series aluminum, they had an assembly of 2 gears and a rotor hub for their propeller arms that were machined out of 6000 series aluminum. So they knew coming to us that we could potentially give them those 20 parts in the time they needed to assemble and test prior to their test with the customer. So the key here was speed. They needed 60 parts in 20 days. Machining couldn't get them there, but the FIM process could. And Clifford will detail a little bit of how, the hours stacked up and how it showed speed over machining.
So we looked at the ability with the Exip machine, we can print all 72 molds in 18 hours. We were able to round that up to 80 molds because we had some extra time in the week. But this speed is something you could not do with just normal conventional billet machining.
So our next case study centers around the functionality that we get out of the FIM process. A lot of prototyping options for advanced materials or even metals really comes down to 3D printing. There are a lot of advantages of 3D printing. We know that we use it for the FIM process. However, when you're 3D printing your final part and it needs functionality, that's a challenge with high performance thermoplastics, especially filled thermoplastics. So if it has carbon filler, if it has glass filler, you don't get fiber alignment from the 3D printing process. You also get a lower resolution. And there are also environmental challenges with it as well. You don't get the same functional output of the material as you would from the injection molding manufacturing process. So with the RPM process, we have characterized the functionality of the HX5 material after the RPM process and shown that it is mechanically comparable to injection molding. It's environmentally comparable. It's thermally comparable. So this is a fully functional prototype solution that you can get quickly. This customer specifically needed to do thermal cycling, and the HX5 material is best in class with any material for its dimensional stability. Its coefficient of thermal expansion is about 1/6 that of aluminum and orders of magnitude better than any other material. So when doing thermal cycle testing on this high sensitivity optic system, they needed the lens mounts, which we were providing, to be highly dimensionally stable over a wide range of temperatures. And on the next slide, Clifford can detail, what we see from the CTE perspective and how we can tune fiber alignment to optimize that feature.
Yeah, so the chart on the left kind of compares our abilities to prototype. You can 3D print PEEK, you can take a PEEK billet, machine it, or you can have the superior material and a molded HX5 part. So that's what we went with. And the picture on the right kind of shows the fiber alignment using Moldex 3D and the ability to gate gate different parts and see how that fiber alignment changes is very important for our customers. This way, the fiber is radial, so actually the part will expand and contract dimensionally proportional throughout the entire part. If you gate it in a different way, it may only expand, contract more in the Y direction than in the Z and Y direction.
So it's really a feature of understanding the functional needs of a part and utilizing our software and predictive analytics to optimize the part. And what's beautiful about the RPM process is going to be demonstrated in our next case study here. But before we get to that, I want to let Clifford talk about the cost analysis that kind of shows you where this fits.
Yes, so the customer only needed 5 of these. And the break-even point is just before 20 parts. So compared to just steel tooling it. So this allows our customer to, one, have a lower cost of barrier of entry for injection molding. and then they continue to iterate if needed to produce different designs or different concepts until they're ready to go to steel tooling. And if they're never ready for steel tooling, they stay below that 20 parts that they're actually going to come out more economically ahead.
Yeah, so this process can be used for low volume prototyping or low volume production. It's just a function of understanding what the cost of those parts are, what the cost of the steel tool would be. And that's one thing we always take a look at when we start this process with the customer, is understanding the program economics and how we can help them bridge that gap without them producing, planning to produce all of their parts from the FIM process. There are cases where the FIM process is always going to be economically more beneficial than building a steel tool, but that's always going to be on a case-by-case basis. So our last case study shows the ability to iterate. It kind of combines the speed and functionality of the FIM process with an added benefit of being able to do design cycles. So this customer was bidding for a defense contract. It was a thermal scope for, again, a defense contract. They came to us with a need for 2 initial prototypes in 30 days. They gave us an industrial designed model, essentially, and we had to help make it manufacturable, print it, and give them functional parts in 30 days. That's a pretty rapid turn for any process when you need to reinvent the wheel in the design process, essentially. But what this process did after that is the customer was able to deliver their prototypes to the end use, the government, for their functional evaluation. And that iterative process allowed us to go back and redesign the second set of prototypes based on that customer feedback that gave them the ability to optimize their design within 3 months, 4 months, basically the entire length of a full steel tool production cycle. So if we go to the next slide, it'll be this shows a timeline of the comparison of what would have happened had they procured a steel tool prior to doing the freeform injection process. And as you see, it's clear they were able to deliver parts well ahead of time and also put a design iteration in there. We like to use this process to bridge the gap to conventional tooling, because for high volume injection molding, conventional tooling is the best way to get a repeatable, stable, output. However, that repeatability means that you're locked into that design. So before you want to lock that design, you want to make sure that design works. And this process, as you see here, we were able to deliver those first 2 parts in 3 weeks. The customer had it for a week. We worked with our customer to develop basically a Gen 2 and produce another 32 parts out of that Gen 2 that were better for the customer based on that initial feedback. And all that happened in a total of 8 weeks, compared to the potentially 12-week cycle to get a part in hand for a customer if we went to production tooling first. So this was the iterative capability of the FIM process.
And being as a part supplier in the engineering department, we were able to then get a whole bunch of knowledge on these parts. How do they fill? What's the shrinkage? What are some of the design problems with these injection molded parts way early? So that when we do go to steel tooling, we know what to look for, what to design for. We are, we've done the tools twice now. Now we go to steel tooling. We have a whole bunch of knowledge now on how to make these parts.
And to put a cost analysis on this, as we were kind of doing with the last case study, is understanding where that crossover point is and how it benefits the customer. So this customer did procure about 40 prototype parts in total. It was 10 sets comprised of 4 parts per assembly. So we ran the math on what the estimated tool cost would be for production tooling based on those designs and what the actual real prototype cost that they paid for is. And you see that they spent 35% of the cost of just production tooling, not production parts, to get 40 prototype parts in hand, again, much faster. So this was a small percentage of what would be a total production budget that enabled them to actually proceed with this avenue and deliver prototypes to the customer that were functional. These were extremely weight sensitive, so our material was key. There were other environmental properties of our material that were important to the function of this thermal scope. So being able to prove that for the customer was paramount, and being able to prove it quick is exactly what we did with the FIM process. So yeah, Clifford can now tell you about how the FIM process works with our high performance HX5.
So HX5 is an extreme temperature multi-scale reinforced polymer with unique freeform injection molding challenges. It has a very high melt temperature, a very high freeze temperature, and it has a significant amount of fillers. The Nexa X-Mold material has a somewhat lower maximum injection temperature, a lower glass transition temperature, and its surface hardness is significantly weaker than the H13 tool steel that we're used to dealing with. Because HX5 is at the upper limit of X-Mold in terms of temperature and abrasiveness, we need a lot of simulation to guarantee good parts with freeform injection molding here at Alpine. So we use programs like Moldix 3D to simulate the mold flow and improve the design of our molds. This is just giving an idea of the temperature differences between the X mold material and an H13 mold base. It's molding considerably cooler. So sometimes we'll run into short shots or cold flows or really poor weld lines using this process. So we'll have to tweak either wall thickness, runner design, gate design to fully optimize for freeform injection molding. And another thing we have discovered is your location of vents is very important. This allows the air to escape from the mold. If that doesn't happen, you'll get an air pocket. That air pocket will then create a short shot within your mold. So we often run two different molding simulations. We'll run one with vents and without vents to make sure that our vents and our air is fully leaving the part. The other thing that we've been doing is we've been making sure that we at least get molten material into the packing phase of the part, into the vents. This kind of makes sure that the part fills perfectly during the injection molding process.
So yeah, to summarize how we benefit and how our customers benefit from utilizing freeform injection molding in our RPM process, it's the case studies kind of outlined it, ideally speed. We're doing high performance parts quickly. So we're faster than the production capabilities. In some cases, we're faster than machining at high quantities. And in most cases, we're going to be faster than 3D printing high quantities. We're functional in this process. So again, we're doing high performance parts that must be tested against rigorous standards. We're dealing a lot in aerospace and defense, whether it's FAR, mil-spec, et cetera. We can do a number of predictive analytics like Clifford was just talking about. We're good at the predictive analytics side, but in these worlds, you need to actually physically test these parts. So functionality of a prototype is paramount. And then the last benefit is the iteration possibilities, to be able to iterate your design multiple times in the cycle of 2 months is incredibly fast compared to traditional methods. And it enables customers who do need to test, iterate, redesign, optimize, go through that cycle multiple times. This allows them to do so in rapid fashion and give them the confidence that the part that they choose for their final design will perform as intended.
Awesome. Thank you guys so much. Before we jumped into the remaining slides, we are getting towards the end of the slides before we get into our Q&A section. So I wanted to remind everyone to please enter your questions into the Q&A box and we'll address as many as we can. And one thing I wanted to point out to you, you guys did a great job of covering how to mold complex high performance materials with FIM and with X mold. So that was really great to see, and particularly how y'all leverage the MoldX software to help simulate those flows and get more information. And so I think that's important to highlight that software plays a key component there in that process, but also the material versatility or compatibility with the X mold. So everything from maybe more basic plastics that people might be familiar with, an ABS or polypropylene or even some silicones and things like that. It's really robust, high temperature, high performance, and highly filled plastics like you guys with HX5. So I think that is something that stands out as unique in the industry, and you guys did a great job of demonstrating that, as well as the benefits of that incredible material. So as we're getting questions in, I know you probably have a lot of follow-up needs as well. So I did want to cover just where you can find some more information. If you visit our website, we have a link here that you can post, and we'll also make this available after the presentation as well. But you can see how not only Alpine are using this, but our other customers as well, everyone from Pepsi to Wilson Sporting Goods to some medical device companies, and how they're leveraging FIM to produce parts rapidly. And also we have a case study with Alpine as well, focusing on another topic that we didn't cover today, and that's how they went from initial tool design to 80 molded components in just 10 business days using FIM. So feel free to check that out as well. And as of course, everyone starts somewhere. So if you are looking at starting this process and you want to dive straight in, Karsten can help you with that. But if you're looking for someone to help with the complexities that you just saw regarding mold design, mold flow, all of those things like that, that is exactly what Alpine is here to help you do. So I did want to emphasize that. And if you want to start with some early understanding, we do have a process and design guide for 3D printed tooling that you can check out. That will help you understand a little bit more about the process and more technical detail for all of our injection molding enthusiasts out there. All righty, let's open up for Q&A. I'm already seeing some great questions come in. The first one, and Karsten, do you mind joining us back on camera? All righty, so the first one is the HX5 material for you guys. It says this has almost 2 times the tensile modulus and flexural modulus compared to a 33% glass-filled nylon, but about 20% higher tensile strength. Is that correct?
Yes, that is correct. And without going into too much, this could be a long labored material chemistry and material composition answer. So I'd like to take this one offline and have a broader conversation with the question asker here. Yeah, absolutely. And we'll be sure to connect you guys. This is another great one. And I will say, I'll throw it to actually both teams here, starting with Karsten, and that is, what's the typical cost for FIM? I think that question's a bit broad, so let's maybe cover what is the cost of the FIM solution all in, as well as maybe an average material cost we might see for a mold, and then going to Jeremy and Clifford to understand what it looks like to get FIM parts or for a single molded component through Alpine Services.
Yeah, it's a good question, and it's a fair one, because it sounds comprehensive when you look at all the value. The good thing is, when you look at what systems are needed in order to doing that, it's literally a printer, an Exa printer, the X mold resin, a clean and cure station, some software, mold generator software, and then to get the part out again, if it's a soluble tool you're printing on the given day, then you need a demolding station. That line we offer for around $20,000 these days for the small zip desktop printer. It looks small, but you can tell that it can do a lot of stuff on the build plane. And then the larger ones, the larger printers will do exactly the same, but they need a large washing station and curing station, and we got you covered there. But at the onset, it's $20,000 to be able to do US dollars, by the way, to be able to get started with everything you need.
Awesome, thanks, Karsten. And Jeremy, how about you guys? Typical timeline and cost for just starting a project and going through the entire RPM process with you guys, which is rather extensive and very helpful. Yeah, so I'll start by kind of saying that while Karsten was detailing what it's like to set up an operation on your own,
we're set up to help you with that operation to mitigate that upfront cost. If you have the capability and want to invest the CapEx to do it, it's absolutely a great process, and I recommend you looking into it and trialing it. But if you want to get a taste for it, or if you have a low volume need or an immediate need, Alpine is set up with this process to mitigate your capital expenditures on this. And typically we see that our parts can run anywhere from $500 to $1,000 per part, depending on how many you order, size and complexity, et cetera. But most cases I've seen, we're beating Proto Labs by about 50% of their cost. And if anyone's not familiar, Proto Labs is a very common prototyping avenue. The one area they do beat us is they might get you your part a few days before we do. But again, it's not going to be necessarily a functional part. It's going to be a form and fit prototype, whereas we're able to deliver a functional prototype at a lower cost.
Absolutely. I do want to, again, give a little bit more credit to the engineering expertise that you guys put into this on the front end, as well as through the entire process. Having come from the service industry myself, I think a lot of that kind of gets skipped over, but you guys have extensive experience with this process with high performance plastics. So particularly if you're looking at parts that are extremely like critical components or anything like that, you're getting a true functional prototype for what I consider a very reasonable cost and exceptional timeline. All right, the next question here is a good one. This gets into dimensional accuracy. This is an interesting one. So what is the dimensional accuracy of X-mold for about a 1-inch part? Are we looking at plus or minus 5 thousandths or tighter? And can we send that to you, Karsten?
Again, a few things taken into consideration. You have a system that is natively born in printing, so you cannot get better than the printer resolution. And there at Nexa we have printers that go from, I think, 46 microns to 72 or 76 microns. So kind of what you get from the printer is what you'll get in the molding tool, which we are really proud of, that the precision in the tool that is printed is directly translated into the part in hand. Then adding to that what material you're injecting and what is the specific design can also make the difference between how precise and how repeatable can you do these things. And are you, by the way, using the same tool, or are you using a sacrificial one-time tool? But when you look at some of the parts that, for example, Clifford and the Alpine team have done, you can see how you can get super near net shape. And if you need an even more detailed level than that, I mean, the parts we showed last week in Austin at the Formnext Forum show there were milled down to, I don't know, Clifford, what was the spec before and after on those parts?
3 thou.
Yeah. And before
we've hit 1 thou, and we've hit 1 thou. It just depends on what was needed.
And straight out of tool, what would the precision be there?
We've seen everywhere from 10 thou to 30 thou. It depends on the part geometry.
Yeah.
And the one thing we do is when we're done molding, we do dimensionally check everything and see if anything doesn't get cleaned up.
Yeah. And it's important to mention when Clifford says we're seeing anywhere from 10 to 30 thousandths, we're using this HX5 material most commonly. We do work in other materials that have lower heats that do get better dimensional stability. But as you get farther away from the TG of the X mold to higher temperatures, you will move the surface area of that cavity a little bit. But understanding what those temperature differences are, how the mold flow will impact that, the general geometry and gate location of the injection process, all those things can be managed to optimize and minimize your dimensional escapes, essentially. And then, like we've mentioned, post-processing is always a way to achieve tighter tolerances if through the film process you're not getting the exact tolerance you need.
Thank you, guys. All right, this is another great question. I'll throw to you, Karsten. We have a customer of ours. Actually, they have an NXE400, and they are a tooling engineer by trade. So they are very comfortable with, molding, but he does not have a tool designer. Do you have any suggestions for him?
Yeah, And thanks for being in that trade. We need you, so let's talk afterwards. In general, all the clients that we meet at whatever stage they're in, they're on a journey to get some part in some design to the next step, the next milestone. So they already have a design file often on hand, an STL file or step file of the part they need. What we have done over the last few years is develop and launch what we call a mold generator software that will allow you to actually convert that part from a step or STL into a printable tool, you could say. So kind of inverting the design part. And it's not a magic tool where you just click on something and then magic appears. It's actually a guided process where we will take you through the considerations worth knowing, because as Clifford and Jeremy said, there's a lot of knowledge captured at every step of the process, all the way from designing a tool, good practices, less good practices and stuff. And I think that is troublesome one if you're not born and bred into the world of tool design or tool making in general. But we felt that pain early on from all kinds of projects, and that's why we have that software. And then again, as Clifford, I think it was you mentioning, you can put vents and gates anywhere you want. I mean, digital tooling is something you do in software until you press print, because then you are printing your tool. So it's, trying things out is less costly and less time consuming. So if it doesn't work in software only, then try it out in real life.
Awesome. Thanks, Karsten. And this is a good one, Jeremy. I think you and your team might have a good view of this, but what is the typical surface roughness you see from an X mold right out of the system?
Yeah, so I think the printer capacity, or the typical finish of the printer, the RA roughness, I think Karsten mentions, is about a 5 to 9. Is that correct, Karsten?
Yeah, it's in that range, yeah.
Yeah, and as far as plating the mold, I'll let Karsten speak to that. But from our output of materials, we found that we get a similar surface finish to the and to the actual tool design, especially with low viscosity materials. They're going to imprint and match that surface roughness. But we've gone through and done secondary processes to clean those, and we've proven that they do coat extremely well too. So surface finish can always be improved very easily.
Yeah, and I think to that note, exactly, Jeremy, that if a client project is all about surface finish, surface quality, and exploring that, then we can early on embed other things into the printed tool. So the beauty about Xmold is that it's a printed tool on its own, but it could also be a printed insert to a bigger steel tool, where it would suddenly now take all the complexity out of the tool design and tool making in a printed block sitting there in the right corner of the bigger tool. And then the rest of the part will have the surface quality and might be in those critical areas where steel is needed. But keep in mind that Xmold and printed tooling can be combined with regular materials like inserted metal pins that be overmolded, or halfway steel tools, halfway molded tools. We've done a lot of that over the years.
Awesome. Thank you, guys. Okay, we're getting some really fun questions that I certainly don't know the answer to, so I'm hoping you guys do. The first is, what would the molding parameters from your process translate to traditional? So in other words, when you move to steel tooling, would you have to repeat the full first article process entirely, or does it help simplify that process as well whenever you're transitioning to metal tooling?
I can speak to this one from specific aerospace and space certifications, and this is going to be the traditional engineer's answer of it depends. Yes, it can mitigate that, and in some cases it can completely alleviate it, but the parameters are different, so it's going to depend on what FAR or mil-spec other requirements are necessary. If they go into the actual processing parameters of the material, then yes, you would repeat the FAI process. However, there are certifications out there where the processing parameters of the material aren't necessarily paramount, and it's all about the mechanical performance of the material. So if you're able to prove it with the RPM or the FIM process, then it could be certified for the other. Again, it depends on which specific certification, but there will be cases where you will need to repeat the FAI process, and there will be cases where you won't.
Awesome. Thank you. And another great question here. What is the upper limit on the size of a part that can be injected, and how complex can the mold be? Can it incorporate slides or more than 2 pieces for a mold?
I can take that one in a few examples maybe. If you look at how big a mold you can do, well, the Zip Pro, our largest resin printer, has a build volume of close to 20 liters, like 19.7 or 19.5, I think it is. But when you look at it, I mean, I can't even show in this camera. When you look at the block or the chunk of stuff you could put on that build plane, XYZ wise, you'll be amazed. Adding to that, you just have to keep in mind that you have a mold unit that is large enough to hold that tool and to fill that tool shot size wise. So that is actually often what we see our clients not suffering from, but are sometimes challenged by, that they can have a big part, but where do we fill it unless we are a full scaled up mold shop and tool shop? On the other hand, what was the other part of the question, Louis, you said?
They wanted to know about multi-part tool designs. Can it incorporate more than 2 pieces? Can it incorporate slides, anything like that?
Yeah, I mean, the native way of thinking with the freeform injection molding and RPM is, if you can get one part out of a tool in the time and at the specs that Team Alpine just showed so clearly and evidently with data, then you are a lucky person right there. If you can get more, you are a luckier person. You can drive down cost and ROI numbers and stuff like that. But what our clients often see, and I put up a few things here on my desktop here, they often work around certain things where they want to work with the different materials. Here we have, stainless steel filled this and that, carbon filled PPA, unfilled PEEK. So they're happy enough that they can just get one part like this impeller in another material here out of a tool like this, because this tool happened to arrive at the right time and the right space and place for them, so they can think like this. So having the ability to get things in hand, as the Alpine team also said, get things and data in hand is an advantage. Optimizing for multi-cavity tools is normally not a big thing, because it's often about a part. It's about those 5-10 validating parts in that week, and then you can have 5-10 other ones next week, but redesigned and optimized from what you learned in the first week, and so on and so on. So it's not built and thought out as we want to do a 20 cavity tool, because honestly, if some of you recall the photos in the slides later, we can print those tools damn fast on those printers. So it might actually end up being your mold unit having a cycle time challenge and not the printers. So yeah, we think differently, but we do it for good reasons.
And then to follow up to that, Karsten, I'm sorry, do you have something to add, guys?
Yeah. So one thing we've found is when it comes to freeform injection molding, that's one of the things that frees you up is you don't need to plan for slides or ejectors. You have a cavity in a mold. It's a sacrificial mold, and you make that mold as small as possible, and then you can fit more on the build plane. So instead of like trying to do a 20 cavity mold, you just have 20 individual prints, and you try to optimize resin and print time based on that. And that seems to be a much better strategy for freeform injection molding.
Oh,
the key of mitigating tool complexity comes from the demolding process, whereas in a traditional tool, when you need those slides, it's because you're mechanically ejecting the part. Here, you're chemically dissolving the tool away to give you that ejection process. So you don't have to have that geometry that allows for mechanical ejection.
And I think I just have one part to back that up exactly, and we showed it last week, and it's a pretty complicated one, but you can see here it's a prosthetic hand grip for a Paralympian, actually twice gold medal winner. But this is the tool with a part inside, and as Jeremy and Clifford just said, getting a tool designed to solve this one, and I can actually show you how the part looks in 30% carbon filled PEEK, and it sounds like this. And it's pretty complicated. And when it's in a 40% glass filled PPS, it sounds like this. These are totally freeform injection molded in high performance materials, coming from a tool where having to print and demold it was not the biggest challenge, because being able to work in materials and exactly very bespoke, actually CT scan designs like these is normally not easy when you move into the molding and the tool design world.
And another great thing about freeform injection molding is that you can compensate for different shrink factors of those different materials too.
Yeah, based on knowing, based on doing, and then based on measuring the things, the parts up, and then adjusting in your next iteration. I agree.
Okay. All right. We are getting close to the end of time here. So first and foremost, Carson, I do want to emphasize something before I get to our last question. And that is, we've had a few people come through and ask about molding press compatibility. So can you elaborate on that a little bit?
Yeah, I mean, that's another beauty of this process, that it is, as the name says, by 66.6%, it's injection molding, right? And then we add freeform in front of that. And that means we handshake seamlessly with the injection molding space. So the installed base units out there will cater for this. It's literally all about having, if you take that part again here that I showed, you anchor this, it's actually from the other end, but that's gone. You anchor that in a mud base, which can just be a very, very basic aluminum tool with a hole in it to keep this carrier that is printed. You inject it and then you pop it out. Those mold units, I mean, we're coming out with a system next week where we will embed a 5-ton mold unit to the desktop solution that we already have. Many of our clients, including Wilson Sporting Goods, they use the 418-ton press here in Hillsborough to do the batch that we've seen online as well. So we just touch and we interact with the mold units out there, and through a very, very basic mud base or cassette you can put on your mold unit. Doesn't need water, cooling, anything. It's just a carrier, a placeholder for the printed tool that can be as complex or as simple as you want it to.
Okay, that was very thorough. Thank you, Carson, and very helpful. We're on our last question, and that is, what type of mold finishes are available? They're asking about EDM, mold tech, etc.
I don't know, maybe Team Alpine, you can elaborate on how you work around these things, how you optimize for these things.
Yeah, so I think what he's getting at is, can you introduce texture to your finished product? You can, to the degree that the resolution of the printer can provide. So the short answer is yes. The long answer is, what's the actual finish you need? It's not necessarily a chemical process, it's a printed process. A lot of your mold tech textures are going to be acid etching or similar, so it's going to be a different process, and it might not be the exact same specification of that texture, but with the resolution of a Nexa zip printer, you can likely get close to almost any of those mold tech textures. I don't know if you have that, or if I just said everything that was wrong.
That it could be done. I think a safer and faster way would just be media blasting at the end to replicate that texture.
Yeah.
Oh.
Yeah, because it's getting that texture through the z-axes versus the x and y. If it's just a flat plate, then yeah, we could print that texture up to the resolution. But as it goes up like a curved surface, I think that would be a bit challenging, and it might distort a little bit. So that's where the media finishing would come in.
All right. Well, that ends the questions that we're able to address today. I did want to tell all of our audience, we had a lot of questions come through, several of which just of the technical depth that we wouldn't be able to get to all of them in this conversation. So we will be sure to pass your questions to all of our experts here so that you can get a more in-depth explanation and address your questions specifically. But also, after we've had a chance to review those, we'll go ahead and pull together some of those most common or impactful questions into a bit of an FAQ document for you guys, so that you have something to reference. So that'll probably be next week whenever that comes out. We also always get asked about the recording or reviewing of the PowerPoint. So that will be sent out within the next 24 to 48 hours. You are free to share that with any of your colleagues or friends or associates that you think might be interested in that. It's not a link specific to you, so you're free to do that. And as always, you have my contact information from the invites, but you will also get the contact information from Carson, Jeremy, and Clifford. I did want to thank all of you guys for attending. When it comes to freeform injection molding, I feel like we are only just scratching the surface of that conversation, and it continues to evolve, and we get deeper and deeper with every webinar that we do. So if there is any other information that you want to hear, any other topics you want to cover, feel free to email them to me. I'll include my information as well, and I'd love to hear that, and we can develop some content around that to help dive into areas of freeform injection molding that you're interested in. To our friends at Alpine, Jeremy and Clifford, thank you so much for all of your help today. It was wonderful to see what you guys do and how robust you've made the FIM process by incorporating it with your rapid prototype molding process and the HX5 material. But thank you everyone for joining us, and have a good day.
Thank you. Thank you, Louis. Thank you, Karsten. And thank you, everyone.